Now let us look into the applications of the heteroscedastic regression model we have just discussed in theory. First is heterosimulate. Um, Consider a heteroscedastic regression model, which is y equals beta naught plus beta 1 xt plus ut with zero mean and sigma square t variation, which is a time varying variance, in which the exogenous variable is IID with zero mean, normally distributed with zero mean and one standard deviation. And as we know, sigma square t is time varying variance. The exercise uses simulation methods to identify the properties of alternative models of heteroscedasticity. Simulate the model 500 t equals 500 observations, where we're going to simulate 500 observations where sigma square is the linear heteroscedastic specification. So we're talking about linear model with gamma naught and gamma 1 omega t, in which omega t is t a time trend and parameter values, initial values at theta naught equals beta naught 1, beta 1 equals 2, gamma naught 1 and gamma 1 equals 0.5, generate and interpret the scatter plots between yt, xt, yt, omega t, y square and omega t, u square, estimated residual with omega t, estimated residual. I'm gonna get estimated residual by regressing y on x. Repeat the process for power heteroscedastic specification. So power model gamma naught plus gamma 1 sigma square t or omega square t. Repeat part A for step heteroscedasticity specification, where d is dummy variable, which is 0 for below 250 observations, 1 for above 200 more than 250 observations. So gamma naught plus gamma 1 dt, and parameter values are as given. So let's see how this equation is estimated heterosimulate. So I'm gonna first of all, let's see if there are any local functions. There are no local functions, so we'll start with simulation. So obviously we'll start with setting the seed, simulate the model 5000 times, alpha, beta, delta and gamma is given to us. So first we are gonna generate exogenous variables randomly, because it's in zero mean and one standard deviation with normal distribution, so random n t1. On the other hand, let's simultaneously look into R. Obviously clear, in place of clear we do all equals true, is all true, least equals is all true, rm, and graphics of, and then for random streams, global stream, in the place of simulation we do set seed 1 and kind Mersenne twister. That's all. So we do heterosimulate with we're putting everything in function. Well, t is 5000 observations, alpha, beta, delta, gamma is given. Random n, which as much as I remember is r norm, so it's a time trend. So I'm x is a time trend, so I'm estimating x. Then omega is also a time trend. So what I'm doing is I'm looking into the equation here. Omega is a time trend, so t minus 1. Omega is t is a time trend, so up until t minus 1 I'm going to estimate omega from 0 to 0.1. I'm going to multiply that to t minus 1, which is going to be generated 4999 times omega t, because it's gonna start from 0 and it will step up until 0.1 at 0.1 stages. So sequence 0, uh, 0.1 multiplied to t minus 1 up until t minus 1. So 0, it will go on at 0.1 for up until t minus 1 stage, right? 0.1 up until 0.1 t minus 1. So omega t is the time trend. This is the tweak. We never tried estimating omega before. Very simple. The sequence starts from 0, goes up until t minus 1 period, multiplied to 0.1 each time. It will increase by 0.1. U is, as we know, square root of delta plus gamma omega, square root of delta plus gamma omega. Well, here gamma not 1, gamma 1.5, we are just telling it delta and gamma for ease of use. So sigma square is delta gamma omega, so square root of delta gamma omega multiplied to again R norm, normal distributed. So we have generated exogenous variable with simulation. We have simulated omega, we have simulated u. We use these all to simulate y. Y is alpha plus beta x plus u. That's it. So we have simulated y. That is all about the first problem. See, we just need to simulate the equations. So up to this point, everything remain. Up to these two remain same. U, we use x and u to, well, update the later parts of the problem. So basically that is heterosimulate, and then plotting we can do manually. We don't need to do with codes. Let's have a look into how R's plotting are. XY, type E is linear, mean is A, X lab, Y lab, limit is not necessary, between L, that's all. So type L, B, T, Y, L, I'm not sure what does that mean. Okay, this is not necessary, just limiting between -4 to 4. We can do it manually if I can recall. So this is heterosimulate. The next problem, see, sometimes the problem seems bigger than the solution. Next problem is estimating and testing heteroscedastic model. Consider the heteroscedastic regression model while y equals beta naught plus beta 1 xt plus ut. Well, ut is 0 mean and variance, which is time varying, in which x is equal to again I, ad is 0 mean, 1 standard deviation, wt is t equal time trend. We already know how to find that. Parameter values, initial values are given to us. Simulated t is equal to 500 times sigma square is multiplicative heteroscedastic specification. Beautiful, no problem. Derive log likelihood function. So we're gonna do it with estimate parameters with maximum likelihood estimation, compute MLE with Newton Raphson, and do the LR Wald and LM test, and we can do it for power heteroscedastic model as well. So before the test, we're going to look into the estimation method, and obviously this time there will be local function. So to begin with, estimation, hetero estimate. All right. Okay. So first, look into the local functions. Data simulation. We in function, the function is simulate data. In both cases, the function is simulate data, where the input is t and it gives us y, x and omega this time, right? So function is simulate data, input t, return will be list x equals x, y equals y, omega equals omega. Fine. So beta naught given to us, beta 1 given to us, gamma naught given to us, gamma 1 given to us. We use it to simulate x, which is simply normal distribution of t. See, t, rows on column, number of columns, not necessary to specify in R. Then omega is obviously 0 to 0.1 t minus 1. 0.1 multiplied to t minus 1, that means 0.1 for 4999 times, with each step going forward at going up at 0.1. This in R we do sequence, use the function sequence from 0 to to 0.1 t minus 1, each step at 0.1. Then u is obviously this is exponential function, so square root of exponential of gamma naught plus gamma 1 omega, and that is multiplied to random t minus 1. So u is again square root of exponential gamma naught gamma 1 into see, there is no element by element specification, r norm t minus 1. Whenever there is element by element, we use simple, because this is a scalar. So whenever we do element by element, so with each element we do simple multiplication. If it is vector, we would do with percentage signs, and then we simulate beta. Fine. Then log likelihood function, negative unconstrained. This is done in a later stage, not a big deal. Log LT, the function is log LT, which gives me b, y, x and omega. Y, x, omega. B is not, beta was not. Now we are going to estimate beta. First, mu is beta 1 plus beta 2x. Beta 1 plus beta 2x, which is basically gamma naught plus gamma 1 x, or omega in this place. So omega can be represented as x. We have learned that in theory. So mean is mu is mean, which is beta naught plus beta 1 x. Bear with me a moment so that I can go back to the theory part of this discussion. So this is very simple. Mu is beta naught plus beta 1 x indeed, and gamma which is the mean, and exponential of gamma naught and gamma 1 is sigma square. So mu is beta 1 and beta 2 x, right? Beta 1 and beta 2 x. Which are the beta 1? Beta 1 is beta naught, beta 2 is beta 1, because these are the unknown parameters. Gamma naught and gamma 1 are also unknown parameters. So square root of exponential beta 3 and beta 4, and we use these for our log likelihood function. Half log twice pi into sigma square y minus mu sigma square divided by 2 sigma square, right? So that is our log likelihood function. Let me see log. So that is the simple log likelihood function. Half log twice pi sigma square coming together, and mu 1 minus mean sigma square, 1 minus mu whole square. So y minus mu divided by sigma square, the regular function, right? We always do this. So half log twice pi sigma square minus mu square divided by 2 sigma square. So that is the log likelihood function, and the negative log likelihood function is unconstrained model. Unconstrained, so return log L, and then neg log 1 is function of theta y x w. So log LT is b y x w. Return log L, we are gonna use log L here, theta y x w minus mean of log LT theta y x w. So b is now replaced with theta. That's all. Negative constraint, neg log 0 theta y x w, mean of log LT naught theta y x w, and by log LT naught we have beta everything except this time omega. There is one gamma, so gamma naught, gamma 1, we have gamma naught, but gamma 1 equals 0. That's all. So beta 4 will be 0. So this portion gamma 1 omega will be 0. Everything else remains as it is. So function starts, there's no tweak here, starts with the third bracket, and then we move on with beta 1, beta 2, beta 3, beta 4, which is 0 now. Everything is the same. So we have constraint and unconstrained log-likelihood function, and we move into model. Now we specify the model to simulate the model. So this is not necessary, we can simply use call the simulate function. It is equal to 500 observations y xw simulate data t. It will automatically simulate y xw in R sim results. In sim results I'm gonna store simulate data, so it has already stored it in sim results. Now y is in y column, x is in x column, but omega is in omega column. That's all. Then unconstrained model, theta initial values are given to us 1, 2, 0.1, 0.1, and by C we are meaning that we are combining 1, 2.1, 0.1 these values to a vector. Then estimate results, where optimization is the par theta initial value neg log 1, y equals y, x equals x, omega equals method BFGS, and Hessian is true. So theta 1 is stored in par, so estimate results at par. LF1 is estimate results value, in the value we have log-likelihood function. H1 is estimate results Hessian, it is stored in Hessian. Now here well, theta 1 log-likelihood function in Hessian, we do fn in nunc at b neg log 1 b y x w theta. Very simple. So log-likelihood unconstrained parameter estimates, square root of, so theta 1 by t square root of diagonal inverse Hessian, which is t value, right? Or what is it basically? Yeah, just bear with me a second. This is so we have theta 1 theta parameters estimated, and also we have the square root of diagonal of the inverse of Hessian, that gives us standard errors 1 by t square root of diagonal inverse of Hessian. So square root of diagonal inverse of Hessian, yes, that gives us standard errors. So we estimate that, and that's all. Your model has been estimated for constrained and unconstrained, and we use both of them, both of constrained and unconstrained estimators, to test for our hypothesis. Is there any tweak that we need to remember? Basically not. It's simple. Then Heterotest. Let's move into have a look into Heterotest, and Heterotest, and here also see this is the same thing, and up until this everything is fine that we have done. Then LR test is taking the difference of simply 2t the restricted and unrestricted model. Constraint model, up until this everything is fine. Standard errors fine. So log-likelihood ratio test, then Wald test 0001 4, and we are testing for if gamma 1 equals 0 or gamma 1 not equals 0. So this is the equation. So row bind, so R equals row bind with 0 0 0 1, where we have combined these and added them with a row bind. So in rows they are represented in rows, q equals 0. Basically they're in rows, not in columns, right? They're in rows and they're in rows. Combine them first, these values, and then use row bind. Bit unnecessary in complication. LM test is theta naught, theta is theta naught and 0. Combine theta naught and 0. Then I need to find GMAT, which is the so I need to find the gradient, numeric gradient of theta yx. Very easy. So mean of the numeric gradient is again in column bind, so column means of the numeric gradient, which is in columns, coming in columns for each parameter, the numeric gradient. Then outer product gradient, or OPG, is J, which is gradient transpose multiplied to gradient divided by T. So transpose gradient multiplied to gradient divided by T, and LM is TG inverse of simply T into G transpose into G divided by, this is LM test, right? LM test statistics, and that is something we have always known. So very simple. LM test statistics, LR world LM. Okay. We can have a look into our note that we have just talked about. So 1, 2, 3, 4, 5. LR. No, this is the next one. World and LM. See LM T G theta, information matrix transpose, and then again G theta. That's all. So then we check for we also do the two-stage LM test, and how to alternatively, how can we do the two-stage LM test fast? Remember, well, we are doing that first. What are the stages? So the steps are to regress y on x, as you can see, if you can remember, regress y on x, find x, and then to obtain residual u, regress u on 1 omega, and compute t r square. And r square is 1 minus e square mu square by mu. Okay, so regress y on x, LM. In LM test, first what we are doing, replicate 1 t times up until t times, and x has been replicated that many already, and then we are doing column bind. Okay, so two different columns. Then y on x is regressed, linear model y on x minus 1. I'm taking the coefficient and stored in B, equals y minus beta x, so u. Then omega is 1's t1 and omega, so we need to regress u on omega, so omega needs to have similar replication. V equals u square, that we already know, v is u square. So u is 1 and omega. Stage 2 regression is beta, when omega is v is regressed on u is regressed on omega. So sorry, v is regressed on omega, and v is u square, right? Yeah, v is u square, because let me show you. Alternatively, v hat can be redefined as u square, right? So that's what has been done here. Hence we use the redefined v in u and regress u with omega t, which has been shown here. So v has been redefined here and has been used in finding omega t. Then e is equal to v. With this we estimate error e, and we use e to find r square, right? And what was r square? Is 1 minus e square divided by v minus mu. Very simple, mean of v. So sum of e square divided by sum of v minus mean of v squared is r squared. Tr square is LM test. So that is what is simple hypothesis testing. And now we move on to the next problem, business cycle. In this problem, data are percentage quarterly growth rates of output, spreads YT and spreads XT for G7 countries: Canada, France, Germany, Italy, Japan, United Kingdom and United States. All sample periods are ending on December 1999, but the starting dates vary, which are given in the data file. Consider the following model of the business cycle, where output growth in the mean and the variance are function of lagged output growth and lagged spreads. So output growth is a function of lagged output growth and lagged spread. Also in variance we see that same thing. Estimate the model for each of the G7 countries and interpret the parameter estimates. Perform a likelihood ratio test for heteroscedasticity by testing restrictions gamma 1, gamma naught is 0. Use the results in part A and B to discuss the role of spreads in determining the business cycle. So let me see. This was pretty easy. Now this time the problem is identified as hetero G7. So we need to go hetero G7 here. Estimate done. So we are gonna need to look into hetero G7. First of all, is there any local function? Indeed, we need to estimate parameters. So we have unrestricted and restricted log likelihood functions. Very easily this is done, where neglog py, p is parameter that is to estimate yxw. Neglog function pysw will be the inputs, where m is p1, p2, x all rows in the first column, p3, x all rows in the second column, because in first column we have the outputs and in second column we have these spreads. Then p4, right, p2, p1, p2, two lags, your p3, p4, yt minus 1, gamma 1, gamma 2. So p3, so p2, p1, p2, p3, p4, p5. p4 is exponential of gamma naught, gamma 1, all rows in the first column. Gamma 1, I think it will be simulated. Omega, if not given, then it will be simulated. So omega, probably this is the exogenous as well. p6, all rows in the second column. Yeah. So all the unknown parameters, then likelihood ratio, point log twice y minus 1 log sigma square, half log sigma square, y minus mu square divided by sigma square, and LT, then minus mean of LT is LF, and this is that will be returned. We should always do this instead of making many functions. And restricted is LF neglog pyx, exponential of p4, because gamma 1 and gamma 2 we are testing for if gamma 1 and gamma 2 is jointly 0 or not, right? Yeah, if gamma 1 and gamma 2 are jointly 0 or not. Fine. Now get the data for a specific country. This is not very important, but yeah, it is nice to know. A function, well, get data is the function which will look into the flag. Input will be flag. If flag 1, we read Canada. Change Canada days January 1961 to December 1991. Trimmer 0. Last 19 is being well, for Canada, just to match dimensions. If flag 2 France, if flag 3 Germany, flag 4 Italy, else if flag 5. So if else if function, if else if else, very simple, and if else if function is very simple. Okay, then we go into the actual equation. Is there any tweak? There is no tweak here. We don't do element by element multiplication in R, as we know. So get the data, growth rate or GDP, and spread, second column, all rows second column, all rows first column. Mean variable X is, first of all, YX. We are doing a trimmer YX. We are making it a well, YX, GDP growth and lag, we are in from both. We are taking YT minus 1 and XT minus 1 and representing by X, mean variables, lag GDP and lagged entire spread, because we are trimming one from the last. So column bind, Y and X, they are side by side presented with this function. Then trimmer is a MATLAB function, 0 1. So variance variable W is X, right? That's why we took all the elements of W for first, because we represent X with W, right? And Y equals trimmer, because this is mentioned in our thesis that sometimes omega can be represented by W. Y equals trimmer Y10, because this is the lag GDP growth and lag interest spread, and this is not the lagged one, but just to match the dimension. YT minus 1 and XT minus 1. T is equal to length of Y. Okay, estimate unrestricted model for 6 rows 1 column. Start is 0.1. I'm simulating initial value with start because we have 6 parameters. So I'm multiplying in 6 rows. We are having 0.1 multiplied to 1. Replicate 1 6 times and multiply that with 0.1. That's all. These are all initialization strategy. Options optimized, large scale of display final. Just don't show me into iteration, just the final. And then beta hat and Loglikelihood function. P neglog py xw start ops. So par neglog yy xx method ww method bfgs par value, and we have unrestricted model estimated. Then restricted model, we don't have gamma 1 and gamma 2, so we have 4 parameters initialized with replicating 1 4 times multiplied to 0.1. and then start neglect yi xx. Now we don't have w because in the second equation w comes with gamma 1 and we don't have gamma 1, so we don't have w. Method bfgs par value and lf naught, and so we do LR likelihood ratio test. Percentage p value is 1 minus p chi square LR degrees of freedom. Here also 1 minus chi square CDF LR and degrees of freedom. Degrees of freedom is simply length of unrestricted parameter minus length of restricted. So if something is missing in between, that is the degrees of freedom, which is gamma 1 gamma 2 here. So chi square CDF p chi-square. Chi-square CDF represented with p chi-square LR DOF. That's all. And that's it. This is an error here. It should be sure. This is a major error. This comes with function heteroscedastic, and the function ends here. Very weird. Oh, sorry, my mistake. This has always been there. There you go. That's it. So heteroscedastic and this running these functions will not only estimate our parameters, estimate the model, parameter estimates the interpreted, and also it does the likelihood ratio test of heteroscedasticity. So if our model is heteroscedastic or not has been estimated with these results as well. So pretty good. Then we can move on to discussing the fourth problem, testing. And now we are going to look into vector heteroscedasticity, or in a system of equation, right? System of equation is discussed in, let me see, 1 2 3 4 5 6 right here, 4 5 6 heteroscedasticity in systems of equation. So let's see. The problem gives us a reduced form equation with zero mean and obviously variance covariance matrix, structural variance covariance matrix, and the gamma, instead of gamma we represented S, which is C dWt. Well, this is just the replication, exact replication of what we have studied here before, right? So B, A, C, D, the values are given to us, okay, where X is uniform distribution, X1, X2 is normal distribution, X and omega is uniform distribution. So 0, 10, 0, 9, estimate with maximum likelihood using Newton-Raphson, construct LR and world test. So heterosystem and hetero estimate is done. We're just gonna look into hetero system of equation. So if there is any local function, indeed first we need to simulate here the data, because there is no data given to us, so we are gonna to simulate the data. So first matrix is given to us, beta 1 alpha 1 beta 2 alpha 2. I always tell you to remember the sequence, the index for words, and C11 C21 C22 D11 D21 D22, and then B is equal to 1. We construct the matrix for 1 alpha 2 D. Then exogenous variable I'm going to simulate. So I'm going to running this function called simulate function here. First I'm giving the data yxw, x is 10 into random t1, 3 into random and t1. So the tweak here must be matrix. First combine 1 minus beta 1 minus beta 1 1, number of rows 2 by row t, matrix. Beautiful. Combine these values, represent them by matrix with number of row 2 by row t. Exogenous. So 10 into random is RANIF, a uniform distribution. When uniform random distribution, maximum will be 1. So and normal random distribution is n, which is RNDN, R norm. So RANIF and R norm. These two are the functions, and they are, I'm representing them with column bind, so they are coming in columns. I'm not combining them. I could have combined them. They could have been in one row, if I put C, but instead of that I'm doing column bind. Omega is also run if, very easy. Then disturbances, I'm gonna I'm gonna simulate U. Well, U is for 1 to T. First I'm gonna store residual for 2 columns, right? Because in this problem I'm supposed to have 2 columns, because I'm supposed to have 2 residuals, right? T rows, 2 columns. Because C dw1 and dw2, or C C1 dw1, C2 dw2, we need them, right? So equals 1 to T array, so zeros. I'm creating array of zeros for C T equals to column. Array of zeros, C T equals to column. The whole thing in MATLAB is represented with zeros. Array of zeros, C T rows, 2 columns. Combining T rows into 2 columns, array of zeros. Then I'm presenting this using this. Then for I into 1 to T, or for I in sequence T, which is 1 to T, L is C dwi, because W, we have how many W's? We have W, D, Wi, D1, 1, D2, 1, D2, 2, C, so many dwi, C dwi. UI for I rows for all columns, because there are multiple columns. I rows. Random N is R norm, RNDN, R norm C, RNDN and RND is R run if. 1 row 2 column multiplied to L transpose. So a random number is generated for 2 column up until L. R norm 2, which is creating 2 values, only 2 values that are multiplied for 2 columns, presented in 2 columns, multiplied to transpose of L. So it will be the size of, you will have size of 2 simulated values of U, which taking L, which this is U. You have 2 U's basically that are multiplied with a random number, which is only 2 random number generated. Simulate the reduced form, so D disturbance and also zeros T. Again, already have zeros. Array 0 C T2, array 0 C T2. We do that, and for I equals in sequence T, y I minus x I inverse b. So this is reduced form approach. Y equals minus x by b plus u by b. So this is it. A bit tricky, a bit difficult, but important to remember. So return L, Y, X, all these are returned from these 2 simulations. And then negative log likelihood function. This is basically done for the ease of use, where LF is neg log theta y x w, function theta y x w. LF is minus mean log LT theta y x w, theta y x w, return minus LF. That's all. Unconstrained. So this is simulate and finding negative unconstrained. Now for unconstrained, we have theta y x t is equal to size of y, first call rows column 1, n is equal to size of y. In the second column, size of n rows y, n column y, first row and column. So 1 minus theta 3 minus theta 1, so minus theta 2 minus theta 4 combined, then presumed with matrix 5, 7, 9, 6, 8, 10. This is the important part. How you represent what will be stored here is what is gonna be represented used for your hypothesis testing. So position of your thetas, which theta is stored where. So again, array 0 c tn, array 0 ct1, I in 1 for I in sequence t, u yb x ax l cw I v ll transpose, indeed ss transpose. This is s, basically ss transpose, then log likelihood function. So this is important because we are doing maximum likelihood on system of equation. We haven't done that before. So not only 0.5 but n 0.5 log twice pi, then determinant of b, determinant of v, variance covariance, then the decomposition, right? So column bind u 0.5 inverse v into I rows on column bind ui for all. So okay, so for all the columns, this is being done for all the columns. Why this should have been simply transpose. This is the tweaking part. I'm not sure why they didn't do. They should have done column bind for this as well, but they haven't. They have just done column bind for this. I'm not sure why the column bind is for this. Anyway, then it return the logl, that's all. Then we go back to our mathematics, where we simulate the data. We give the initial estimates, and then we optimize regular without regular optimizers, and then we extract the data. Then variance covariance is represented with inverse of Hessian, and then square root of diagonal of variance covariance give us, and variance covariance gives standard errors. Then word test. Remember where the thetas are located. Just put ones for those thetas, rest is 0. Very simple, because I'm just restricting gamma 1, gamma 2, that's all. So gamma 0, gamma 1. So we basically what I'm restricting here is vector heteroscedasticity. I want to check if for vector heteroscedasticity. So what I need to restrict here is simply, let me show you. The diagonal elements here, d11, d21, d22, these are what I'm trying to restrict, because they are the well, diagonal elements of the variance covariance matrix. So this is what they are dw, right? Because I'm to restrict w. C is gamma 0, d is gamma 1. So I'm restricting this. So where are they located? In these locations, right? This is the number of theta you gave them in the function. So theta 6, theta 8, theta 10. So they are ones and rest are zeros. Simple. Yeah, and then we are doing the word test like that. Degrees of freedom is number of rows in the restricted model. So we do p cos chi square for test. Degrees of freedom are chi square CDF chi square, well, WD degrees of freedom, or test and degrees of freedom. That's all. This is in system of equation. This has explained for the system of equation. Then comes the problem of monetary policy and asset market volatility. We have a problem called monetary policy. The problem suggests that there is a data consists of T is equal to 2583 daily observations from October 1993 to December 2003 for the US on 8 daily bond deals with maturities ranging from 3 months to 10 years. So we have 8 bonds where maturities are ranging from 3 months to 10 years, and they are expressed as percentage. Also contained in the file are equity prices and dummy variables corresponding. The dummy variables correspond to Federal Reserve Open Market Committee meetings, which are the event days. When the meetings happen, they are the event days. So event day when there is a meeting, non-event day when there is not a meeting, to investigate the effect on asset price market volatility. So we have 8 daily bonds with different maturities. We have equity prices. We want to see effect of monetary policy on asset market volatility, because monetary policy represents when there are meetings happening. Consider the heteroscedastic regression model. Variance is based on step function sigma squared exponential of where is the change in the yield. Ith bond D is the event dummy variable corresponding to the meeting date. Compute mean, sample mean and variance for each bond corresponding to event and non-event date. Estimate model for each bond. Use the estimated model to compute estimates of mean and the variance on event and non-event days and compare these results. LR-Walden LM test restrictions are gamma 1 is 0 and beta 1 is equal to gamma 1 0 respectively, two different. And then also bond deals are replaced with equity returns and combined 8 bond market deals and equity returns in parts. Estimate a vector heteroscedastic model. Let's see, it's a lot of things to do. Let's see how this is being carried out. So hetero event. Alright, here we have hetero event. First, the local function. Local function is unrestricted and restricted log-likelihood function. So the equation is very simple, just like before. Mean is beta 1, beta 2, D, which is the mean is beta 0, beta 1 D, and exponential of beta 3, beta 4 D. Very simple. Then the equation is also very simple. Then we take the mean. Unrestricted, restricted case, we have beta 1, beta 2 D, and there is no beta 4. That's all. So variance is just beta 3. Why? Because we don't have gamma 1 dt. So D is also missing from here. We need to remember that, and then we move into this doing the math, because we don't need to simulate anything. We just load the data. Okay. And we pull data, we define the variables. Most of the time goes in explaining the data here because it's a lot of data. So housekeeping takes a lot of time, a lot of the weight of the analysis here. Then change in yield is simply 1 0 minus 0 1, which is yt minus 1, 1 0 0 1. Change in yield, see, same in both cases. Return, New York Stock Exchange, the return requires just the logarithm, but change in yield remains the same. Fine. All rows on column. D, trimmer event. So D is again event day, which is not the T minus 1 period. This is a T period. T minus 1 is this 1 0. So I'm just making sure the event days match the dimension. Then X, ones, length of Y, and 1, because this one row less in this, so, and up to D. So replicate 1 for length of y time, once length of y time, replicate 1 y times d, column bind them, they should be in column, that is x, and length of y. Compute descriptive statistics on non-event day. When d equals 0, that is non-event, I'm extracting data now. When d equals 1, that is event. Beautiful. When d equals 0, that is non-event. When d equals 1, that is event. So I'm just doing some descriptive statistics. Mean of the regular data mean of y minus mean of y, that's all. Unrestricted model must be estimated with MLE. Starting values based on OLS. So first, y is x is regressed on y, LM y regressing on x minus 1 coefficient. Balls have the coefficient. Then ut y minus x beta hat, that's all, and square, mean square. So these are initial values. Basing on these, let's do the maximum likelihood estimation. Beta sigma square starting is 0, beta sigma square, and unrestricted for beta sigma square and everything, 0 for d, right? So large scale of displater, we don't need this many things in our estimate results. Optim start neg log 1 YYDD method VHS SCNT. So LF1 and variance covariance matrix gives us inverse Hessian. We have the estimated model with unrestricted model. Now for the restricted part, there's a bit of estimation. Event day is beta hat 1. What happened? Okay, estimate of the mean is beta hat 1 first row and second row, beta hat 1 first one, third row and fourth row. So mean estimation, so we have means first and then variances. So I have 2 means and 2 variances, beta naught, beta 1. So event day and non-event day. In event day we add up beta naught, beta 1. In non-event day just beta naught, because non-event day doesn't have d. Beta 3, beta 4 in non-event day just 3. That's it, very simple. Then unrestricted model, we don't have d, so that's completely 0. So we just estimate the rest of the beta and sigma square, and if it happens here in event day, 0 beta naught 0 for event day, 1 and 2 added together because there are event days, but d is 0. So let's see what they're trying to do. Beta naught and beta 1, beta hat naught and beta hat 1, 1 and 2. Okay, just like before, only in case of volatility they remain the same for event and non-event days, because here restriction is against this, not this, right? Restriction again is against gamma 1, that's all, because the problem suggested to put restriction for gamma 1 and also on beta 1. So another problem, we can do it on beta 1. So likelihood ratio test, world test. Yes, obviously the fourth element is having equals 1, so column bind, they are coming in column, and then we do this. And LM test, 2-stage regression. First be x on y, you represent with u, right, and x is w and v is u square, then w on v, v on w, you have e is simply e square divided by v minus mean of v square, tr square. So p values is lm1. That's all. 1 is the degrees of freedom. Or you can find the difference between, there is one element that is one parameter that is reduced from restricted from unrestricted, that is y. Or you can simply take the difference between restricted and unrestricted log likelihood functions estimations, and then you see what is the degrees of freedom. Very simple solution to a very large problem, exact repetition of previously, no tweaks at all. Okay, just to see in the log likelihood function, do we do column by, oh, in world test, in world test, whenever I'm doing world test, no, I'm not doing column bind here. That was a interesting thing. I'm not sure in previous example why I did column bind in the last portion. So pretty easy, right? Alright, if there is more, testing for vector heteroscedasticity and autocorrelation. I don't think we'll go into great moderation because that is the same problem. There's so many problems here. Okay, I'll go on for a while. Let's see how much I can cover. So the problem suggests simulate the bivariate heteroscedastic model with autocorrelation for t is equal to 2000 observations with the given information. Estimate model with maximum likelihood using Newton-Raphson. Construct LR and world for joint heteroscedasticity and autocorrelation for vector just for vector heteroscedasticity. So autocorrelation is included here too. So which means the problem is the last problem what we were talking about before. Let me show you. The problem we have already discussed slightly. LR world and LM. Sorry. Not this one. Not this one. No. Here. See, joint world test we are talking about when D's and rows. So where D's are located and row 1 1 1 2 2 1 2 2 will come simultaneously. That's all. You need to know in heterogeneral. So first, data simulation function is created just like before, no tweaks. Then our runif and R norm, W is, runif and R norm, runif, W is runif. So column bind, we did column bind, they are coming in column. We do column matrix function by row, T number of row 2. Then zeros replicate 0 CT2, right? Not replicate, sorry, array 0 CT2. This is the array function, not the replicate function. I'm sorry. Array 0 CT2. So S CDWI V random and runif. No, R norm. Sorry, random n is R norm. First row, two columns, right? Just one random number generated twice multiplied to L transpose L times. That's all. So row 1 ut minus 1, row 2 ut minus 2, row 1 1, row 1 2, row 2 1, row 2 2. That's all. This is the tweaking part. This is the important part. Reduced form, simulate the reduced form zeros. This is the only difference for which we are doing this problem. Okay, everything else remains same. return list yy xx ww negative unconstrained theta y xw unconstrained log likelihood function. We represent everything with in the matrix, again locating where each parameter will be, then zeros, array 0 ctn, zeros is array 0 ctn, then 0 0 zeros, t1 array 0 ct1, that's all. Then uy beta y plus ax vi ut minus rho ut minus 1. This is the regular autoregressive residual which is equal to ut minus rho ut minus 1. L is cdwi, v is ll transpose, or I can just suggest it as s. Then the log likelihood function as before, nothing changing. Then lf is simply trim the log to remove make the dimension equal, because we have removed one array in all this calculation, so one array is fixed here. Return log l, that's all. I don't think the trimming is required here for r. That is a different thing, interesting. It is a bit of a tweak, I can say, because it is interesting. I don't need to adjust the dimension, it automatically probably adjusts the dimension. Okay, so these are the local functions. Then I'm just gonna go into doing the math. So simulate for, and then doing the math is doing the problem is simply simulate the model, call the simulated model, simulated, bring in the simulated results, introduce the initial parameters, then just do the optimization, do variance covariance, which is then standard errors are adjusted, then comes the word test fault. Q T column bind replicate, Q is replicate 0 by number of row. Interesting. Replicate, we could have just simply done that, but okay, sure. Replicate 0 how many times, number of row times, and do that column bind. Fine, not bad. Degrees of freedom is number of rows. Good. Easiest way to express chi-square, CDF, or p chi-square. That's all. Beautiful. We just needed to bring in the autoregressive portion in our functions, which is basically this. That was the only part for which we did this problem. This is one, and the V autoregressive estimation has been included. This is essential, indeed important. This is not an ignorable thing. So you do two U's instead of just randomly finding U's. You do two U's, UT1, UT2, and then you use those U's right here. Important. And in function you do V and you use up that V. Where do you use this V? Yeah, in the log likelihood function. These are the two important thing here. Okay, heterogeneral is done. Not bad. There's a problem of great moderation. The exercise is based on annual data on real US GDP per capita for the period of 1946 to 2006. The great moderation refers to the decrease in the volatility of US output growth in the early 1980s. Moderation, they have the volatility of output growth decreased to its best. This proposition is tested by specifying the following model. and exponential in which what is growth rate in real GDP. It is dummy variable defined by two periods. Construct the growth rate, estimate parameter model. US GDP growth rate has become less volatile in the post 1983 period. That requires gamma 1 to be less than 0. This is the second challenge, right? Gamma 1 is less than 0 because gamma 1 has decreased significantly for the rest of the period. Which goes to negative. So heteromoderation, is there anything there? Beta 1 is 0 or not? Heteromoderation. Let's see how this problem looks like. Basically, what do we do? Okay. Negative log likelihood function. We do that if flag. So we have a flag. If flag is constraint, flag is set against constraint or unconstrained, right? Yeah. And where am I setting the flag? Not setting the flag anywhere. Okay, I'm just creating the function like that. If I'm giving flag, then it is unconstrained. If I'm not giving flag, then it is constrained. Fine. Unconstrained or constraint. If giving flag, why am I doing byx flag neglog, right? And in flag we do fm in search sigma square. So I'm testing for why? Because there are two tests. I'm testing for beta 1 is equal to 0. Yeah. So in first case, if there is not flag, beta 2, I'm not going to estimate beta 2. It will be beta 3, beta 4. So I'm not going to estimate the second part. I'm not going to estimate the fourth part. I'm not going to estimate the second part again. 0 is, that's all. Yeah, this is the great moderation problem, so maybe this is how it is. Okay, flag is set against dummy variable. So basically, if there is flag, then we have both the periods. If there is not flag, so after the post moderation, before demoderation, that's why two different mu and sigma. Define the log with beta 1 unconstrained and constraint 0d. Okay, beta 1 0d, beta 3 beta 4, beta 4 0d. So d's for unconstrained, this is when d equals 0. In both cases d equals 0. Okay, constraint for beta 1 0, each observation log at each observation. Okay, and then we do the regular maths. From first housekeeping, estimate the unconstrained. Exactly same, estimating the unconstrained, estimating constraint model is just the flag thing. Here nothing else. LM test, rest to everything else remains same with beta 1 0, beta 1 0 flag. Flag, that's all. Oh, I'm giving flag unconstrained model. FM flag equals 1. Flag, I'm not giving flag. That's all. Two different estimations are coming for post and pre. That is the tweak. Everything else remains same. Tiring. So just two flags and estimate twice everything with respect to flag 0 and flag 1. That's all. When is flag 0, your D's are 0. So you don't have dummy variable. That means this is post. Flags are 1. This is pre when there is dummy variable. That's all. One more thing to see. Grid moderation. Let me just have a look into one more thing. How are they handling the vault test when it's less than 0? That is statistics for less than. Okay, there is nothing actually to mention that. Stage 1 LR test statistics, everything else. There's no tweak anywhere. It doesn't really matter. I don't think they have done that bit when so it's just the flag thing, I'm sure. LR vault test 1, LM regression form, vault test beta 1 equals to 0. Here beta 1 equals 0. Here gamma 1 gamma was 0, and the last element was 0. D was 0, where beta 1 0. This is telling you the whole story, nothing else. In the functions, how did we set in the functions? Just the flag, that's all. If there is flag, in both cases D is 0. If there is flag, then we have beta 2x. If there is not flag, we don't have beta 2x. For unconstrained, we have gamma, the last element D is constraint, we don't have the last element. If flag, we have beta 2x. If not flag, we don't have beta 2x. So this is the tweaking part, and that's all. Okay, great. Now it's clear. Okay, then sampling properties of heteroscedasticity estimator. Heterosampling, you have exogenous variable. We need to simulate model with different observations and compute mean, bias, mean squared error. Sampling distribution with 100,000 replication. Gamma 1 equals 0. See, let's see, heterosampling, right? Heterosampling, obviously log likelihood function. We'll start with log likelihood function pyx, because we have beta naught beta 1, gamma naught gamma 1, by and x. p y x. Beta p has beta naught, beta 1, everything y and x. And p1, p2, p3, p4 exponential. Fine, very simple. Then comes replication. How many replication? Oh, simulate the model 500 times. Beta, everything is there. We have theta naught. Combining this, array and is runif. 100,000 replications. So we'll create 100,000 rows. Array row. So 0 C end rows, 4 end rows. Monte Carlo replication. 4 for 4 parameters. ML 0, theta LS zeros. Text progress bar. K equals 1 to n. Okay. K equals 1 to number of draws. So create the loop, begin the loop. Then we generate data u, square root of exponential gamma 0 gamma 1x. That is multiplied to r norm. Good. Then with that we multiply beta 1 beta 1x. Generate data, use generated data for estimated parameter estimation. And then we do OLS for we generate I mean with the replications. For the replications we do what? Mean squared error, maximum likelihood estimation, least squares. Basically it requires us to do everything. So population parameters are estimated with maximum likelihood, and then we need OLS as well. So we do OLS here. To find E log mean square theta OLS is gamma and beta and 0, gamma beta and 0. So that will end the total progress, 5,000 replications, root mean squared error, everything. That's all. Very simple.